Einstein's quantum explanation of the photoelectric effect. Prior to Einstein's explanation, scientists believed in the classical wave theory. By classical theory, radiation was distributed uniformly to the electrons, which caused a time lag for sufficient energy to be absorbed to escape from the metal. Furthermore, classical theory believed that sufficient light intensity could allow electrons to escape, regardless of frequency of light. Therefore, light of higher intensity can increase the kinetic energy of an ejected electron. The problems with the classical theory included no time delay existing, as the emissions were proved to be instantaneous. Furthermore, there was found to be a photoelectric threshold, the minimum frequency or maximum wavelength. This also led to the discovery that the emissions of electrons and the maximum kinetic energy are frequency dependent, opposing the classical theory of the dependence on intensity. Nonetheless, the classical wave theory did correctly predict how the photocurrent was proportional to the intensity of light and how the number of photons were proportional to the intensity, but for the wrong reasons. Now this was where Einstein came in. He built on German physicist Max Planck's work on quantum theory proposed in 1900 to explain what the classical theory could not. Einstein proposed that light consists of packets of energy in finite quantities called photons, defining light as a particle as well as wave. Rather than energy spreading uniformly across the electrons of a metal as proposed in the classical wave theory, all the energy of a single photon is manifested into a single electron. This discovery allowed Einstein to develop the work function, a minimum energy per photon required to emit the electron from the surface of a particular material. It is shown as minimum work, phi, is equal to Planck's constant times threshold frequency. Einstein also explained that when a light quantum had more energy than required, the excess energy would be transformed into kinetic energy for the electron emitted. This is shown by Einstein's photoelectric equation. Maximum kinetic energy equals hf minus phi, where hf is photon energy, the h being Planck's constant and the f being frequency, and the phi symbol is the work function of the metal. It is graphically represented as shown, where the gradient is Planck's constant and threshold frequency is indicated by f0 for each respective metal. Therefore, an increased frequency of the light causes an increased maximum kinetic energy of the electron, and vice versa. Therefore, the original photon energy can be calculated through energy to get up to the surface plus energy to go through the surface, or the work function, plus kinetic energy with which the electron is liberated. This is graphically shown as follows. Green represents the energy required to get the electron up to the surface, the red indicates the work function, and the blue indicates the kinetic energy of the electron. It is observed that if the electron is deeper into the metal, more energy is required to get it out, and hence it gives it a lower kinetic energy. Einstein's quantum explanation still has a continuing impact to modern day life. One of the most important developments this has instigated is solar cell technology, which uses the photoelectric effect to transform sunlight into electrical energy. Therefore, Einstein's quantum explanation of the photoelectric effect has outlined the nature of light in having dual qualities of waves as well as particles. He had answered the questions classical wave theory had failed to answer. Thus, his work on the photoelectric effect proved to be an invaluable contribution to science to the present day.
Created using Powtoon.